There seems to be a ramen craze sweeping the US lately. No, I'm not referring to the instant ramen packages you find in the grocery store aisles. I'm referring to the fresh ramen noodles served in a delicious hot broth the chef has been preparing for days, topped with slices of pork, veggies, and a ramen egg. In Japan, we call these soy sauce marinated eggs ajitsuke tamago or ni tamago. Most commonly eaten as a topping in ramen, these flavorful eggs are soft-boiled and marinated in a chef's secret soy sauce-based marinade for a particular amount of time. But how long does that take?
In this experiment, we'll be modeling the diffusion of dye and soy sauce into the whites of an egg. We'll accomplish this by placing eggs into a solution of diluted dye, concentrated dye, and soy sauce. We'll be taking timed measurements of the cross-section of the eggs and measure how far the respective solution has penetrated the egg white. This experiment was performed at two different temperatures, one at room temperature, 25 degrees C, and another at fridge temperature, 2 degrees Celsius, to determine the effects of temperature on diffusion. To prep our eggs, we boiled 48 eggs for 15 minutes and deshelled. The eggs were then cooled before placing them into the colored solutions. A large batch of each solution was prepared. The dilute solution had a ratio of 3 drops of dye per cup of water. The concentrated solution had a ratio of 6 drops of dye per cup of water. And finally, the soy sauce solution had a ratio of 1 cup of soy sauce to 3 cups of water. Finally, 1 egg was placed into each cup of solution. At 1, 2, 3, 4, 5, and 10 hours, a cross-section was taken of 1 egg, and the thickness where the blue or brown color stopped going into the egg was measured. An average of 4 measurements were taken for each cross-section. The cross-sectional measurements were taken every hour for the 3 solutions at room and fridge temperature.
The model we have selected involves the time-dependent diffusion of species A from a surface at constant concentration into a semi-infinite medium, as shown by this graph. As we can see, into the egg, as time increases, the concentration increases as the boundary layer travels into the egg.
We're using the dynamics that are found in the transient diffusion in semi-infinite medium, and we're applying this to our hard-boiled eggs with soy sauce and also with blue dye as concentration A. We have 3 main assumptions here. 1, that the fluid is stagnant since it's in cups and not moving. 2, there's no reactions because the dye/soy sauce is just going through the egg, it's not doing anything to it. And 3, the egg is a semi-infinite medium. The eggs are pretty big compared to how far the fluid's going to diffuse through them. So first we have to start with our equation of continuity. There's no velocity because the fluid is stagnant. We're also assuming only diffusion in one direction, so we can cross these out. And there's no reaction. So we get to simplify a lot. So first we have to go over our conditions. Our initial condition is that the concentration of dye is 0 at t equals 0 because we're rapidly going to drop the egg in dye. First boundary condition, concentration of dye is equal to the bulk concentration at the boundary of the egg as soon as it's dropped in. Our second boundary condition is that at x equals infinity, the concentration of the dye is 0. Next, we're just gonna math.
Based on these assumptions, we follow the derivation of the final equation relating time, concentration, depth of diffusion, and the diffusivity coefficient from Dr. Ted Lee's notes from Lecture 7.
Woo! As you can see, we also have a slightly complicated version, but it can simplify down to theta of eta equals 1 minus ERF of eta. Remember that theta is Ca over C bulk. However, when we take all of our measurements, we're going to be finding wherever the dye or soy sauce front ends, which means Ca is actually going to be 0 at that point, making theta 0 at that point.
From the complementary error function curve, we see that eta is equal to 2 when theta is equal to 0.
Which is what I have written here. Okay, so now backtracking a little, we have that eta is this equation, and we have these as our variables. We're just gonna math, rearrange. We can plug in a little more. This gorgeous equation this is how we're going to find the diffusivity constant. Because if you notice, it actually looks like the equation of a line. If we make x squared y and we make 16tx, then the diffusivity constant is just the slope. And this is how we're going to find the diffusivity constant in all of our trials. Done with the math. We're moving on.
approximately 10 hours and 36 eggs later. We classify this experiment overall as a success. We hypothesized that reduced temperature would show reduced speed and diffusivity, and that increased bulk concentration would increase the diffusivity. As shown in the temperature charts, the warmer room temperature solutions diffused farther in the same amount of time as the cooler experiments. This link between higher temperatures and higher diffusivities is further supported by the actual diffusivity results, where all three measured diffusivity constants for room temperature were higher than the constants for the cooler temperature. Thus, part of our hypothesis was supported by our results. However, the other half of our hypothesis was not supported by this data. As shown in the overlapping concentration curves between the high and low blue dye concentrations, bulk concentration had a negligible effect on the diffusion speed in the eggs. However, it was observed that the higher concentration dyed the egg a deeper blue as it traveled into the egg, instead of both concentrations resulting in a similar blue hue as expected if the diffusion speeds were constant, as measured. We recommend further experimentation to investigate the obvious difference in concentration of dye as seen in the different blue hues as the color front travels into the egg, and more experimentation over a larger range of temperatures. Well, hopefully these results help a master ramen chef prepare even tastier eggs, with better efficiency too. And hey, we applied our chemical engineering knowledge. Yay, mass transfer! While we don't recommend eating these eggs, go enjoy some ramen for yourself.